There's this idea that feels like it's pulled straight out of a sci-fi movie, taking our data centers, our cloud infrastructure, and putting it all into orbit. I mean, can you imagine the cloud literally floating among the clouds? It sounds like the absolute next frontier for tech, but why aren't we doing it? On the surface, it just sounds like a no-brainer, right? You've got access to pretty much endless, unfiltered solar power. You don't have to buy land or deal with zoning laws. So why aren't the big tech companies in a frantic race to launch their servers into the cosmos? It seems so logical, but as we're about to find out, the idea crashes into some very, very harsh physical realities. So first, let's just take a moment to appreciate why this idea is so, well, awesome. In orbit, the sun is just blasting out a steady 1,360 watts of power for every square meter. No clouds, no nighttime, no atmosphere getting in the way. You could totally sidestep huge Earth-based problems, like needing tons of water for cooling or fighting over land use. And physical security? Good luck trying to casually access a server that's floating thousands of miles above your head. It all sounds fantastic, but this entire beautiful dream is built on one single, fundamental misunderstanding. It's an idea that's so common, it feels right, intuitively, and that's the idea that space is cold. It feels true, but it's dangerously wrong, and it's the very reason this whole concept just shatters when you look at it closely. And this gets right to the heart of the physics. See, a vacuum isn't cold like your freezer is cold. A vacuum is just empty. And because it's empty, there's no air, no matter, nothing to carry heat away from a hot object. A vacuum is actually one of the best insulators in the entire universe. It's the exact same reason your thermos keeps your coffee hot. Down here on Earth, when something gets hot, we have three pretty good ways to cool it down. You can touch something cold to it, that's conduction. You can blow air or run water over it, that's convection. Or the object can just radiate its heat away as infrared energy. But in the vacuum of space, you can just throw those first two options right out the window. They're gone. You're left with only one single option. And that one option you're left with, radiation, is just terrible at its job in this situation. At the relatively cool temperatures that our electronics love, around a nice 27 degrees Celsius or 80 Fahrenheit, radiating heat away is an incredibly slow and inefficient process. The servers would basically just be sitting there, stewing in their own waste heat. And this is where the scale of the problem just becomes, well, absurd. To cool just one kind of small 10 megawatt data center in space, you would need to attach a radiator to it with a surface area of 25,000 square meters. That is the size of almost 4 professional soccer fields, just for the cooling system. Can you even imagine trying to launch something that massive and delicate? And that, right there, reveals the central flaw in the whole plan. Everybody focuses on the wrong thing. Getting power from the sun in space? That's the easy part. The real, fundamental, laws of physics roadblock is getting rid of all the waste heat that power creates. That's the true bottleneck. So you'd think that a massive, physics-breaking heat problem would be enough to kill the project, right? Well, that's really just the beginning of the issues. The problems just keep piling up, making this sci-fi dream more and more of a practical nightmare. Okay, let's just pretend you magically solve the heat problem. Now, how do you actually use the data center? Here on Earth, we've got this incredible fiber optic network. In space, you're stuck using lasers, which have way less bandwidth and, way more importantly, much higher latency. A signal to a geostationary satellite and back takes at least a quarter of a second. Boom, right there, you've killed real-time web browsing, video calls, online gaming. It's all gone. The only thing it's good for is offline batch processing jobs. And what about when something breaks? A memory module fails, a power supply dies. On Earth, a technician drives over and swaps the part in an hour. We call that mean time to repair. In space, there is no repair. The whole philosophy has to change to mean time to replace. That means you have to launch an entirely new multi-million-dollar satellite just to fix one tiny little problem. The cost is, well, it's astronomical. On top of all that, space is basically a shooting gallery of high-energy particles. You have cosmic rays, solar flares, constantly bombarding your sensitive electronics. They can cause these random errors called single-event upsets, literally flipping ones to zeros in your data. Now, you can shield against this. It's called radiation hardening, but it's expensive, it adds a lot of weight, and it actually makes your processors slower. Now, I know what some of you are probably thinking. Okay, fine, deep space is hard, but what about low Earth orbit, LEO? It's closer, the latency is lower. And that's a great thought, but believe it or not, choosing LEO actually makes the biggest problems even worse. So this right here, this is the absolute deal breaker for LEO. A single orbit only takes about 90 minutes. But for about 35 of those minutes, every single time it circles the planet, the satellite is plunged into the Earth's shadow. That's a complete power blackout for over a third of its life, over and over again. So to keep a data center running through those constant blackouts, you'd need a ridiculous battery system. We're talking hundreds, maybe thousands of tons of batteries just to survive the orbital night. It creates this impossible choice. LEO's power is unreliable, but a higher geostationary orbit with constant sun has that crippling data latency. There's just no perfect orbit for this job. When you get right down to it, LEO fails spectacularly at the two most fundamental things a data center needs to survive: continuous, uninterrupted power, and a way to get rid of its own heat. For high-density computing, it is literally the worst of all worlds. So after you stack up all the problems, from the brutal thermodynamics and the slow data links to the impossible maintenance, the constant radiation, and the fatal flaws of LEO, the verdict becomes overwhelmingly clear. For pretty much everything we use the internet for, our home planet is and will be the superior platform. Now, does that mean the whole idea is completely useless? Not quite. There are some very specific, very niche cases where it actually could make sense. For example, if you have a satellite that's gathering enormous amounts of raw data, it might actually be more efficient to pre-process it right there in orbit, shrink it down, and then send the smaller result home. But for the general purpose cloud that powers our websites, our databases, our AI, it's just a non-starter. And that really leaves us with this one big final thought. The grand vision of a data center in the stars isn't being held back by a lack of engineering skill or a lack of ambition. It's being held back by the fundamental laws of thermodynamics. So the question really becomes, until we can figure out a way to break those laws, is the future of our digital world forever grounded right here on Earth?